All right, so 9.6 is on exponential and logarithmic equations. And I have here the steps for solving these equations. Just like we've done for absolute value and square roots and things that are squared, or even just trying to solve for x in a linear equation. We want to isolate the log or exponential, just like we'd want to isolate the square root, or we'd want to isolate the squared term to be able to use the square root rule, or being able to isolate the square root of something so that we can then square. So here we want to isolate the log or exponential so that we can deal with its meaning. And then we might be able to evaluate it right then and there. It might be in a format that we can find the answer. If not, then you change forms. So if it's a log, you change it to an exponential, and if it's an exponential to a log. Sometimes your values are too big to use them directly, and so you might need to expand or simplify the properties. Sometimes you have your unknown in more than one place, and so you need to simplify it in order to put it in one spot. So you'll see a couple examples of that. And then from there, you solve. So either you can solve it in the format it's in, or you need to change forms and then you can solve. And then there is the potential for extraneous solutions. Again, bases and arguments must be positive. Typically, we don't see many issues with the base part, but the argument is often the extraneous solution that will come into play. So make sure your argument is positive. So again, for the changing of forms, if it's a log, you do b to the y is x to get it to be the exponential. If it's like this, the base, and then you say base to b to the y, so base to the y equals x, and fill in the blank, or just know that the idea is that you're getting your exponent to be by itself when you're dealing with logs. So this first case is kind of our new scenario that we haven't had to do yet. How would you do this? Well, you want to take the xth root. Well, what is the xth root? You can't take an xth root of 125 and get a value, and x wouldn't be by itself anyways. That was the whole reason we started dealing with logarithms. So we're stuck in this format. So we're going to change it to a log and see if we can then evaluate it. So this is log base 5. 5 to the x is 125. Now this expression has no unknowns, so we can find the value of it, and we will have solved for our unknown x in the process. So to find this value, you could say 5 to what power is 125, and you might know that that's 3. But what if this was like 120? Then there's not a nice integer. So it's good to be aware of how to solve this generically, and that is the change of base. Log of 125 divided by log 5, or if you have a TI-89, you can use the Diamond 7 feature and do log 125 comma 5, and then close your parenthesis and enter. The other option is, instead of writing it in log form, to take the log of both sides. And so if you'll end up with log 5, the x can come down in front. So x log 5 equals log 125. This your calculator can handle because it's base 10. You don't even need to worry about change of base there. And then to get x by itself, you divide by log 5. But you'll notice that you've essentially created that change of base anyways. Log 125 divided by log 5. Same expression, just two different ways of approaching it. Writing it in log form or taking the log of both sides. Case 2 for exponentials is where the unknown is the base, in which case we undo the exponent to get the base by itself, to isolate the unknown x, that's the base. So take the cube root in this case, and you get 5. Remember, there is an nth root button on your calculator. Some calculators have a cube root, some do not. Most calculators have a square root though. But again, not everything is squared. So you need to know how to do an nth root. So if this was a 5, you know how to do it. And then lastly, case 3 is if the exponent is here for your exponential, like it equals that, it is the answer. And so, well, there it is, it's the answer. It's just whatever 3 squared is. So in this case, you just evaluate straight off the bat, and you have your answer. So you've seen now where the x is an exponent, a base, or the answer to the exponential. Changing forms helped you when you were stuck otherwise. Otherwise, you basically evaluated like normal. So what if you have it as a log? Well, if we're stuck because you cannot type in your calculator log x divided by log 2 and have it solve for x, and you can't just like divide by log base 2 of nothing because you need to have it of something. So the only way you can get the x by itself is literally changing forms. Do 2 to the 5th is x, and then you can evaluate. So far we've kind of just talked about how to do them in the basic cases, but what if it's more involved? So isolate your log. So in this one, I had to subtract 1 first. Then it was 10 to the 4th would equal this quantity, x minus 3. And I evaluate with our standard processes. 10 to the 4th is 10,000. Add 3 to get x by itself, and your answer will be 10,003 equals x. So that was if the unknown was your argument for your logarithm. The next example is if the unknown is the base of your logarithm. So first isolate, so I divide by 4, and now that it's isolated, I'm still stuck. I don't know the value of x. X to the 3rd is what? You might be able to think it out, go what to the 3rd is 343, and know it's 7. But again, that's what you're saying to yourself. It's x to the 3rd. What to the 3rd is 343. And if you don't happen to know that 7, you can use the nth, in this case, the cube root, to undo the cube. And the last place is that your argument, that your unknown could be the exponent of the exponential or the answer to the logarithm. And in that case, you just need to evaluate that left-hand side. So again, sometimes you can evaluate right away. To evaluate this side, because you do not have base 3 in most calculators, you could use the change of base, log 9 divided by log 3. Or in the 89, you can actually say log 9 comma 3 and parentheses enter. Now, sometimes you get lucky and you don't need a calculator because you can say to yourself, well, 3 to what power is 9, and know it's 2. All right, so this example over here, the log is isolated. I can find the value. There's no unknowns of this. So log base 10 of 10, log 10 divided by log 2. So these are both invisible base 10. You can also use the ln button. Log base 10, like change of base can be, you can make it base 10 or you can make them both base e. And base e would be the ln button. And the nice thing about that is that the 89s have an ln button right on their main keypad. So you, instead of saying log 10 divided by log 2, you could also say ln 10 divided by ln 2. In any case, you get 3.3219 as an approximation. I had to round, and I rounded to the nearest 4 places. Now, I'm actually going to caution you not, you can write this down to help you kind of process, but if possible, you really should be keeping the entire decimal in your calculator, subtracting 5, so you keep the entire thing that's longer than this in your calculator, then divide by 3, and then at that point round. So this was just more for showing my work, but I'm actually keeping the entire thing in my calculator because I don't want to create a rounding error and then another rounding error and compound my rounding errors. So as long as I keep the entire thing in my calculator and just hit -5 and divide by 3 without retyping it or clearing my calculator, I'm going to get a more accurate answer. So I've got a lot of practice problems. We can't evaluate this because the x is here, so we're going to change forms. 2 to the 6th is 4x, evaluate. 2 to the 6th, 2 caret 6 is 64, dividing by 4 would give me x. Here we already have equals x, so I just need to figure out this value, and I can do that by change of base. Can't find this value, need to get the x by itself, so I'm going to change forms. X to the -5th is 1/32. There are a couple ways to approach this. One option is to rewrite this with positive exponents. You can then either cross multiply and get x to the 5th equals 32, or you can realize that the numerators are the same, so for the fractions to be equal, if the numerators are the same, so should the denominators. For example, 1/32 has to equal 1/32, so x to the 5th has to be 32. To get rid of the 5th power, we take the 5th root. We get 2. Here's an example where we have x in 2 different parts. Well, we can't really do like x to the 2nd equals, well, where do we go? Or this expression to the 4 to this equals this, and you can't ignore that. And we can't find the value of either one of these 2 terms because they both have an unknown in it. So we need to combine them. So addition, when we combine into a single log, is the same as multiplying the arguments. Now that it's a single log, and I went ahead and distributed it, I'll have 4 to the 2nd equals x squared plus 6x. I can evaluate 4 squared is 16. Then I notice I have a quadratic, so to solve a quadratic, I want to set it equal to 0. So I subtract 16 to both sides, so there it is with a -16. To solve a quadratic, if possible, I prefer factoring method, but you can also use quadratic formula, or you can even use completing the square and do the square root method. But typically, factoring or quadratic formula is easier. So what multiplies to -16 and adds to 6? 8 and -2 do. Since the a is 1, I can go ahead and just say x plus 8 times x minus 2. So my 2 solutions would be x is -8 and x is 2. Now, because our x was, our unknown was part of the argument, we do need to make sure that it's positive, that our argument is positive. The variable can be positive or negative, but the argument itself must be positive. So if I plug in -8 here, my argument would be negative. It would also be negative here. If I plug in 2, it's positive, and then I'd have +8. So the 2 is fine. You can even check your work and make sure that it gives you an answer of 2. This is more of a property. You can do this a couple ways, but if you recognize they have the same base, so the exponents must be equal, that's a cool trick to save you some work. Alternatively, you can take the log of both sides, and you can then bring down the exponent. And so you'd have x plus 1 log 2 equals 6 log 2. Divide both sides by log 2, and you end up with x plus 1 equals 6. So x is 5. The bases are not the same on this one, so you can't quite do the same shortcut. However, if you can rewrite it so that they have the same base, then you can end up doing that same rule that we just did. You can see that these both 27 and 9 can be written with base of 3. And an exponent to an exponent, you multiply. Exponent to exponent, you multiply. And then you can say, well, the bases are same, so the exponents must be for these two to be equal. Or you can do what I was mentioning on the prior problem, and that is to take the log of both sides. Or rewrite it as a log. So this one was rewritten as a log. It's a little more involved that way, but it's log base 27 of this equals that. So 27 to the 4x plus 10 equals 9 to the 39th. That's exactly what I have here. 27 to the 4x plus 10 equals 9 to the 39th. Now, this is quite large, 9 to the 39th for your calculator. So bringing the 39 in front will help you evaluate. In fact, you might still want to break it up even more, find this value, and then multiply by 39. And eventually, you will end up getting 26. You will then subtract 10 and divide by 4 to get x by itself. So here's one where you've got multiple terms, but this time the x is only in one of them. So you could evaluate, but at this point you're already getting an approximation. There should probably be an approximately equal at this point. Unless, of course, you're keeping it all in your calculator, and then it would be equal until the very last line where you approximate. If you kept it all on your calculator exactly, you should get exactly 500. If you end up rounding at some point, you might get something very close to 500, and that's just because of the rounding error. So one way to avoid some of that rounding error is to actually put them together. And again, the invisible base is base 10, just like it was here. So 10 to the 6th would equal 4x squared, dividing by 4, and then square rooting. Get you exactly 500. Okay, 7 to the 18th is too big for your calculator, so you'll want to expand it. So use your rules. If you have an exponent, that becomes a coefficient, and then I can isolate my log, and now all of a sudden the situation is a lot smaller. It's just 7 to the 3rd rather than 7 to the 18th. It's still equivalent, but it's able to be then solved using your calculator. 7 to the 3rd, 343, dividing 23, and then dividing by 4. So those were all log problems and some exponential problems, mainly logs though, because that is the main point of this lesson. Exponentials are something we've already done. So now I want to discuss natural log and E situations. So basically, whenever you see ln, you could rewrite it as log base E, or just put an E as the base. So we cannot take the natural log of this because there's an unknown. And in order to isolate it, the way we are going to do that is changing forms. So whenever you're stuck, change forms. So e to the 7th is x plus 5. Well, e to the 7th is approximately this. Subtracting 5, you get your approximation. Okay, isolate your exponential. So add 5 and then divide by 7. Now my exponential, my base to an exponent, is isolated, at which point you can rewrite it as a log base e, or just ln. So e to the 3x is 5. So ln of 5 is 3x. ln of 5, you can type it into your calculator and divide by 3. Or you can take the natural log of both sides, and this 3x will come out in front, and then this is a value of 1, because e to the 1st is e. So no matter how you think about it, and you can actually type it right in your calculator, not this particular one as an x, but something else, like you can do ln e to the 5th, and you should get 5, or ln e to the 6th, and you should get 6, or ln e to the 20th, and you should get 20. So ln e to any power is just that power. And again, that's coming from the exponent, could come down, and then ln e to the 1st is just one of those key properties that we talked about in the 9-4 lesson. It's just 1. So same answer, either approach. Writing as a log or taking the log of both sides. There's an exponential or with the x in the exponent. Isolate it, and then we cannot get x by itself without going into log. So again, we're stuck, so we change forms to log. Log base 5, because the base is 5. 5 to the x is 18. Then we can evaluate this using change of base. Isolate the exponential. We're stuck, so write it as a log base e, or take the log base e of both sides, or otherwise known as the ln of both sides. So we have here log base e. We can just write it as natural log, and evaluating that. Or you could do log of 7 divided by log e to the first. There's just a lot of extra pieces because you have to put it into the first. And so writing it as ln saves you some extra typing. So ln of 7 is this. We add 2 to both sides, and we get the value of x. Okay, ln e to the 21st, I mentioned this earlier. Ln and e essentially cancel and give you your exponent. You can find the value of this. There's nothing unknown about it. You can just type in your calculator and it'll give you 21. So then you can subtract 21 from both sides, and then you could say e to the 24th. That might be a little big, so you can use your rules of exponent or rules of logs, bring the exponent as a coefficient, divide, and now e to the 4th is much easier for your calculator to handle. E to the 4th is approximately 54.592. Number 16, isolate your log. Isolate your log further, change forms, and then isolate x. You can evaluate this and do the regular process, or you can combine them so that there's less rounding error. Sometimes it's good to have it split up because it's too big otherwise, but if it's not too big for your calculator to handle, combining it can result in less rounding errors because you're already rounding here versus here you're not rounding. All right, these have x's in both places, so you do need to put this together as a single log. So log base 3 of x to the 5th divided by x squared equals 6. You can simplify this, or you could say 3 to the 6th equals this whole thing, but you might as well simplify first. So that's 5 minus 2 is 3. There are 5 x's in the numerator, 2 on the bottom, canceling 2 out. You're left with 3 in the numerator. So x to the 3rd is a numerator. We're stuck, so we change forms. 3 to the 6th is this. You can maybe recognize the cube root, and the 6 would be 6 divided by 3 is 2, so you can get 9, or you can evaluate this and then take the cube root. The order is up to you. And lastly, number 19. It's a single log, but it is a quadratic in here. When we do 5 squared equals this, we're going to have a quadratic to solve, so set it equal to 0, factor if possible. Now, I did this one because I wanted to reiterate that your variables can be positive or negative. It's just that the argument has to be positive. And when you plug -6 in for your x's, you will end up getting, say, 36, positive 36 plus 37. It would be bigger than this negative 6 times 8, the negative 48. So it ends up still being positive when I put it in here. -2, so that'd be 4 minus 16 plus 37, still positive. And you can check that it works, again, by plugging in and just making sure that log of that divided by log 5 is 2, or that, or that this is 25, because 5 squared is 25, and it should equal this argument. So I hope that helps with your solving of logs. There's really 6 cases. I recommend that you do kind of a write down notes with the main 6 cases. Again, those 6 cases are when the unknown is an exponent, write it in log form. When the unknown is the base, write it as an exponential. Base of the exponential, my goodness. When the unknown is the base of the exponential, take the nth root. When the unknown is the answer to an exponential, evaluate. When the unknown is the argument of the logarithm, write in exponential form. When the unknown is the base of logarithm, write in exponential form. And when it is the answer to the logarithm, just evaluate. So basically that all boils down to isolate, evaluate if possible. Some of them you could evaluate right away. If not, you have to change forms, and then you can evaluate. Lastly, check for extraneous solutions. I hope that helps you with your solving of log and exponential equations.